Hello. All right, I think we're going to get started here. So first off, a big welcome to everybody, and thank you for coming. I think it takes some commitment to be here at 4:30 on Thursday. So thanks for that. I'm Vidya Srinivasan. I run engineering and operations for Amazon Redshift. And I'm going to be co-presenting this session with Timon from Neustar, who's Director of Infrastructure there. I'm just going to be covering a very brief overview of Redshift, what the platform is all about, and why it is relevant for ad tech, and then hand it off to Timon, who's going to talk to us about the journey that Neustar has had with this platform for analytics, and especially talk to you about some best practices around using it. So hope you find it interesting. So let's get started. So we released Redshift as a service 2 reinvents ago, the very first one, on Valentine's Day. Actually, it went GA on Valentine's Day last year. And this is a petabyte scale SQL data warehouse for AWS. And we really conceived of this with 3 basic principles. We said we wanted to build something that was simple, fast, and cheap. So let's just take that apart. What do we mean by simple? We wanted a data warehouse that would be super easy for you to understand, to deal with, and use as a customer. And we spend a lot of time internally to figure out how we can remove all the friction that you have to deal with, whether it's with creation, whether it's with querying, whether it's getting your data in or managing. And really, we wanted to build this not just for the DBAs. We wanted to build this for the developers, the engineers, the data scientists, because we just want to unleash that population and give them access to data in an easy way. So simplicity is a big part of what drives our design and architecture. The second thing is fast. So I'm yet to meet a customer who tells me, please make my queries slower. That just doesn't happen, right? Everybody wants things faster. You put more data in, and you have less time to compute. Redshift being an MPP system and a columnar system helps quite a bit with ensuring that whatever you're running gets done quicker, faster, because you have so much resource dedicated for every query that you run. So that's fast. And the third aspect is cheap. Well, that's just everybody's on a budget. And what we wanted to do was give an offering that would be disruptively priced when we launched last year. So for Redshift, for example, you could create a cluster and pay as low as $1,000 per terabyte per year. And this is compressed storage, and it's a managed database service. So it was a fairly competitively priced. And we also give a bunch of different options for you to adjust prices. That I can talk about that in a little bit. So let me just quickly dive into the architecture. The Redshift is a cluster architecture. And when you create a Redshift cluster, you're going to create one leader node and any number of compute nodes. The leader node is responsible for 3 things. It's responsible to be the SQL endpoint for all the external clients. So this is what your BI tools will connect to, or any of your PostgreSQL clients. And it's responsible for communicating with them on one end and with all the internal nodes on the other end. And we would never allow an external client to directly talk to internal compute nodes for security reasons. So the leader node also stores all the metadata for the cluster. So this is where we store the catalog, system tables, et cetera, that stores state about what data you have in the cluster. And furthermore, the leader node also coordinates query execution, meaning it takes the incoming SQL, it takes it apart, parses it, figures out what's the most optimized query plan for it, and then generates the code that needs to get executed. This code then gets shipped off to the compute nodes. Now, the compute nodes is where all your data is actually stored. And it's stored in a local storage in columnar format. Local storage because we want direct attach disks, meaning the bandwidth that you have to move data from the compute to the CPU is pretty high. And in general, with data warehousing, the goal is to minimize I/O. So columnar is for the same reason. Local storage is for the same reason. And the interesting feature or the characteristic of this architecture is all the major operations that you do with your cluster happens in parallel across the compute nodes. And that's really what gives us the scale-out nature of Redshift. So what does that mean? So when you're doing inserts or when you're doing loads, either from S3, DynamoDB, EMR, or by doing SSH, behind the scenes, the compute nodes will all work in parallel to go ingest the data. Same thing happens when we do a backup or a restore or a resize. Anytime we are moving a lot of data around or crunching data, we actually do everything in parallel. Same thing happens for query execution. The queries get, part of the query gets executed in each of the nodes and then gets aggregated to the leader node, and the results get sent out. And this entire thing is on an HPC network. We use a 10 gig minimally oversubscribed network internally to connect all these nodes. The compute nodes themselves comes in two types of instances. There's the HDD or the DW1, which is a magnetic spinning disk. And in this case, you can start with a 2 terabyte node and go all the way up to a 2 petabyte cluster. A 2 petabyte cluster comes when you use 128 nodes. Or you can go with the DW2 instance type, which we launched earlier this year, which is basically gives you more memory and CPU, and it is SSD storage. And you start with a smaller data set size. It's 160 gigs all the way up to 2. OK, that's wrong. It's 328 terabytes. I should change that. So how do you decide between the two? It's going to depend on the data set size. If you have really a couple of 100 gigs of data, SSD may be a better bet. The other thing that affects the choice is with SSDs, you get about 5.5 times better performance. You get 5.5 times, it's 5.5 times more expensive, and it's about 10 to 15 times better performance. So it really boils down to the price-performance trade-off that you're willing to make, which one you want to pick. All right, so let's talk about some of the ad tech use cases that we see in use with Redshift today. So I'm sure you're all familiar with all of these terms. But the fundamental thing here is, across all these use cases, essentially what you're trying to do is to figure out what ad to serve, who saw the ads that were served, how much did that cost, and then what action did the user take when they did see that ad. And you want to bring all this information back into your analytics system and then figure out what the next step should be and how you're going to optimize your system and just be more effective overall. And we've had a number of customers use it in for different use cases. So for example, Accordant Media uses Redshift in the context of real-time bidding. So the bidding itself happens using CloudFront and DynamoDB, but Redshift comes into play when they're trying to train their models based on what already happened. AdTheorent and Fixu, they use Redshift for mobile ad optimization. Aggregate Knowledge or Neustar, we're going to hear about quite a bit from Timon. Mixpo uses Redshift for video advertising. StrongView uses Redshift for email marketing campaign. But anyway, I didn't want to go through everything. The point I'm just trying to make is we've seen a lot of adoption in this space, and we've seen usage in a lot of different use cases as well. And we'll be happy to get into details of any one of them. So if you think about why is that the case, and why is it an interesting platform for ad tech, it really boils down to what the needs for the ad tech segment is and how Redshift can actually satisfy them. So what we're dealing with here is typically a lot of data. You need to get this crunched in a fairly short amount of time because you want to use the analysis for taking action before the next day comes or before the afternoon or on an hourly basis. And you're on a budget to figure this out. Budget in the sense you have to justify the need to store and analyze all of this data from a business point of view. And if you think about how Redshift operates and how we've designed the service, with a lot of data, you can actually go for 160 gigs all the way to 2 petabytes within a single cluster. Or alternately, you can actually create multiple different clusters, and it's pretty unlimited how much data you want to store and use. The other point here is we use S3 as sort of the data hub, where most of the loads happen from S3. And given this setup with S3 as the data and Redshift as the computation engine, you can pick and choose what data sets go into which clusters and mix and match how you want to analyze your workloads. And I'll talk a little bit more about this. If you look at the budget side of it, one, it's priced at you can go as low as $1,000 per terabyte per year. And hopefully it makes decisions around what data you want to keep versus what data you have to throw a lot easier. And hopefully you don't have to sample data, but rather run your queries across the entire data set. Furthermore, the other thing that we've seen our customers do, because we allow you to store your backups and resurrect them into clusters very easily, one of the things that people do to keep costs under control is they'll spin up a cluster when they want to do some analysis and spin it down. So for example, in the weekends, several customers spin down their clusters because they're not actually crunching anything. And just the ease with which you can bring it up and down makes this very easy to do. And the third component is time. Again, we do crunch queries quite fast. We're about 10 times faster compared to row-based data stores. And we are an MPP system, meaning you can add more nodes to give more resources for your queries and potentially speed that up. The other thing you could do is you could use SSDs, which again speed things up by 10 to 20 times. Furthermore, one of the requirements we got specifically from our ad tech customers is there was a willingness to trade speed for accuracy. So we started introducing approximate functions. I'll talk a little bit more about that, but essentially the goal there is to provide you with different tools and options so that it's easy for you to make those trade-offs, particularly depending on your workload and what you're trying to do. I'm just going to quickly cover a few functions that are relevant that we see as being in use by our ad tech customers. One of them is the approximate count distinct function. This is based on the hyperlog algorithm, and essentially it gives you about 10 to 20 times speed up, and we say we guarantee a maximum error bound of 2%. In a lot of our internal workloads, at least when we've done this test, typically it ends up being less than 1%, but theoretically it's a 2% limit. And it can help you very quickly figure out basic stuff like number of unique visitors, unique impressions, etc. So pretty handy function to have. The other feature that's used quite a bit is copy from JSON. So we have customers who have a lot of JSON data coming in. And what we allow with this feature is to take your JSON stream and then decompose that into columns within the Redshift table. If it's a direct mapping, you can use auto, or you can actually specify a mapping in a JSON paths file that we'll use to map your JSON data to Redshift columns. The third feature that this is a requirement we've been hearing, and we just announced this feature yesterday. It's currently not fully available. It's going to be available pretty soon. Essentially, this feature is a multidimensional index using space-filling curves. And the problem that we were going after here is what we currently support with respect to sorting is a compound sort key. So in that case, what you end up doing is you specify a number of columns, and we will sort it based on the order in which you specify. So it's one compound sort key. The disadvantage of this sort of a key is when your queries come in without the leading sort column, the performance of the sorting is not all that good because you don't have the leading key. Typically, data warehouses have solved this problem with the use of projections. So basically, you will store your set of columns in different sorted orders depending on what you think your queries are going to come in, and you will use the appropriate one at runtime. The problem with projections are, one, there's a space overhead because you're actually storing the same columns in multiple different formats or different orders. And number two, which is a bigger deal for us, is that we'll now have to maintain the same data, and there's a huge maintenance overhead. When you do updates, inserts, deletes, you just have so many locations you have to go and make sure everything gets corrected. So instead, what we did was we came up with sort of an intermediate solution where we said, we're going to create an index whereby we actually interleave all the bits that you provide as part of your sort columns. And we are going to create a minimum and maximum bucket for that key and maintain that. Essentially, what this means for you is you can specify from 1 to 8 columns as indexing columns, and we will internally create these indices for you. But as far as querying goes, each one of these columns is treated as a first-class citizen, meaning you can specify any subset of columns and still see a performance gain. You're not committed to always specifying the leading column. So the performance gain here varies quite a bit. When you have a larger data set, you will see a lot more performance benefit over the compound sort key. If you do specify the leading column, the compound sort key still gives slightly better performance. So there's some nuances around how to get the most out of this feature. And the last one that I wanted to highlight, more as a way that you can use the platform, more so than a feature as such, is around how you can use it in the context of managing a large number of clusters. So one of the things that I've pointed out earlier is, one, it's easy to create clusters, and it's easy to create not just it's easy to scale out, meaning you can add more nodes to a single cluster or create a lot of new clusters. The other thing that's available to you in terms of raw data is all your backups are stored in S3 and available to you. And all your load data is also in various S3 buckets typically. Now, what this affords you to do is just various different use cases. So for example, let's say you wanted to create a QA cluster. It doesn't have to take, or a pre-prod cluster. It doesn't take weeks to do that. All you have to do is maybe take your production cluster, a backup of that, and just do a create on that. And that takes about 3 minutes. On an average, our cluster creates at about 3 minutes. So it's a very quick way for you to get that done. Another thing this affords you is you can now create separate clusters for each one of your customers or each one of your workloads. And because of the way we price, you get an exact dollar amount for how much you have to spend to maintain that. So it could be $65 a day. And then now you can make some smart decisions around, well, is it useful for you to now keep that up? Do you get enough value out of it? Or do you want to shut that down? So that's the other benefit you get from a setup like this. A third benefit could just be around, well, you might have one big cluster with a lot of workloads. And maybe there is one day where you have to get all your results in half the time for some reason. One other thing you can do is quickly take part of the workloads and run in a different cluster and speed up the time it takes to produce results. Anyway, there are multiple different possibilities. I think all I wanted to point out is you have some building blocks here with respect to backups, your data, and just the ease with which you can manage a single cluster or multiple clusters that affords use cases and that affords a behavior that might be different than what you're typically used to. Something to think about. So with that, I'm going to hand off to Timon.
Thank you. Am I all set? Great. So over the course of the next half hour, I'm going to talk to you a little bit about some of the products and platforms we built for online ad analytics at Neustar, how Redshift has helped us and made it possible and opened up new horizons for things that weren't previously possible for us. So first, I'll take you through 4 textbook ad tech problems that our customers really wanted answers to. Then I'll show you how we solved those problems with Redshift and share with you the design lessons we learned along the way. And then finally, I'll talk to you about some of the operational advantages Redshift affords us and how it's allowed us to execute on new ideas that weren't possible in the past. So let's go through our 4 problems. The first is, how many ads should I show you? Understanding the correct number of ads to show is critical because obviously you don't want to upset people and you don't want to waste money by showing them too many ads. But on the flip side, you also want to reach your audience. You want to make yourself known. And this problem is often called the frequency problem or the optimal frequency problem. So the second question is, how much should I pay for ads? And some ads are more effective than others. If they're working better than others, you should probably spend money on those and not the poorly performing ones, obviously. So this class of problem is called attribution or attribution analysis. Third question is, how do I reach this group of people I'm interested in seeing for less money than I pay to reach them right now? If you can reach the same people for less money on some other site and some other place on the web, you should probably reorganize your spend to reach them there and not on the more expensive places. And this is called computing overlap, right? And so our final problem, probably the most vexing, the most problematic one that no engineer or product manager wants to hear is, could you just run us a custom query? And obviously this goes by many names, but we'll call it Adhoc here. And I'll tell you a little bit about how we solved that. So for each of these 4 problems, I'll go into the question and dig into the core of it a little bit. I'll give you some scale numbers in production to set your expectations. And then I'll cover a simplified version of each solution so that we get our footing. Then we'll talk about the prod challenges and how we solve them. And finally, I'll give you rough estimates of execution times on certain clusters. And hopefully, I'm going to draw some parallels to canonical data warehousing problems so the non-ad tech people can get an idea of what we're talking about. So let's go to our first problem, which was frequency. How many ads should I show you? And deciding the right number of ads to show varies by advertiser, obviously, because you have different criteria, right? Some people are interested in maximizing the number of purchases while staying under budget, yet others want to drive signups. Third group might want to maximize profit. But regardless of what your criteria are, this is fundamentally a cohort analysis problem, right? We're asking the question, did the behavior of the people who fall into the cohort of people that saw n ads differ from those that saw n+1 ads? And cohort analysis basically boils down to a multi-stage aggregation. First, you aggregate to decide which cohort each person falls into. And then you take those cohorts and you aggregate once more to put together their activity into some type of ROI metric. So in our case, we need to compute the number of ads each person saw in order to define their cohort. And then we want to aggregate once again to produce our ROI metric. Now, the wrench that's thrown into the works here is that when I say a person or people, I actually mean unique cookies, right? It's a random number we put in the cookie of a user in their browser. So when you account for multiple devices, multiple browsers, cookie churn, Firefox automatically deleting all the cookies after 7 days, you actually end up with a pretty significant number of people. So for a quarter, that's about 20 billion people. That's a lot, right? So with that kind of limitation in mind, let's go through the skeleton SQL of this and kind of understand why that's ostensibly a hard problem. So in this example, let's say we're trying to optimize for profit, and I've magically assigned each impression a cost and a revenue value based on last touch attribution. Don't worry if you don't know what last touch attribution is. Just imagine I know what the cost and the revenue driven by each impression already is, an impression being a view of an ad for those people that aren't in the ad tech world. The first stage of this query computes the number of ads that each person saw and also sums up the cost and revenue, right? So this is straightforward. We're just saying, hey, for this date range, go group by user ID and accumulate the number of impressions every single user saw. Then the second stage is take all the people who saw n ads and accumulate their statistics together, right? So we're just taking the common table expression, frequency intermediate, and we're pivoting it and reaggregating by their cohort. Pretty straightforward. Now you may be thinking to yourself, well, that's a pretty big aggregate because it's computed, it's a group by on the user ID. And like I just said, for a quarter, that may be 20 billion people. So that frequency intermediate CTE is going to have 20 billion rows. But my answer to you will be hey, that's not actually big enough because that was just the skeleton query. In reality, if you've run an ad tech, or an analysis report, you're going to have different date ranges. You're going to have to segment by campaign and by site and by all these other things. So it's actually significantly more than 20 billion rows that are going to have to go in there. So in reality, what we're doing is saying, hey, that's already a big number, but if we ran it off of the raw data, the raw impression rows, there's about 200 billion of those in a quarter for us. So it's not practical to run those every time for, say, 6 different date ranges for all kinds of different segmentations on the raw data. So in production, in order to speed things up, we materialized an intermediate aggregation in a way that could support those needs. So let's go look at what that intermediate aggregation looks like. So effectively, this table speeds up our computation of our cohorts by partially aggregating each user's activity by day, by campaign, and by site. So what that allows us to do is to efficiently scan certain date ranges courtesy of the first part of the sort key. So we've ordered the table in such a way that we can, if we're only looking at the last 30 days of data for one of our date ranges, then we can quickly eliminate the rest of the quarter. But if we want to run the whole quarter, we can just scan the whole table. And then our segmentation and aggregation to get the desired cohort criteria comes thanks to the last 3 columns in the sort key, right? Now, I've added these extra facets to this intermediate to support these business use cases of segmentation and different date ranges. But the downside is that by adding these extra facets, we end up with 3 to 10 times more rows. So for a quarter, I quoted 20 billion users. That translates to about 70 billion rows in this table. But as I mentioned earlier, it beats the pants off of aggregating 200 billion rows of raw data each time. So this is great for speeding up the query, but it has another added benefit that I like to talk about. So this type of aggregated intermediate can be built incrementally, day by day. So I can basically pull in a new day's worth of data, squish it down and insert it into this table every single day, and I won't have to do a vacuum because this preserves the sort order of the sort key, right? Because by definition, the new day's worth of data has a greater record date than all the previous days. So that's a really big added benefit. Not only do I get to build this up incrementally over time, but I don't have to run a vacuum. So I find that tremendously useful. So what does that intermediate translate to in terms of our final query? Well, it should come pretty naturally. First, we've widened the grouping, right? So we're now grouping by user ID and campaign ID and site ID so we can understand per campaign, per site, what that user's cohort is. And then we're basically using the other table. So this is very straightforward. I mean, this is basically the stuff we run in prod. So you could take that and put it on your cluster and get real results out of it. So without being too abstract here, or rather not to be too abstract here, and to get to something concrete that you can take back home, I'm going to give you a taste of how long this takes to run for a small part of our workload daily. So updating the intermediate takes about a minute a day, and that's taking several billion rows of raw data and aggregating them down to that frequency intermediate table. So it takes about 65 seconds. So we go from that couple of billion to just under a billion rows that get added to this table every day. Then we compute the cohorts for 90 days. So we scan that table of 70 billion rows, and we compute people's cohorts, and that takes just about 10 minutes. So we're going from 70 billion rows down to maybe 20 billion rows, right? Because I said for a quarter we have 20 billion unique user IDs, so I got to roughly get it down to that first. And then finally doing that final aggregation to go from 20 billion rows to a couple of million output rows for our analysis takes about 11 seconds. So all in all, it takes 12 minutes, not bad. And in the context of our full workload, where we run it for 6 date ranges and 2 different types of groupings, and all of our clients at once, hundreds of advertisers at once, takes about 2.5 hours on a big 8 big node SSD cluster. And just for perspective, on demand, that's going to cost you a cool $96. And yeah, it's cool to attach a dollar amount to this, but we learned more than the fact that this is actually cheap to do. We actually learned that it's cheap and really, really, really easy to do. So these massive multi-stage aggregations are actually our bread and butter. They're so easy and so fast to implement correctly that we use them everywhere. They're the gimmies in all of our reports. This is the simplest possible thing we can do. And it's quick, it's easy, it's straightforward, and I barely think about it when I'm computing the complexity or the cost of a marginal report. These are the things I tack on to make reports possible. This is the simple stuff. So we learned that, hey, don't be afraid of big aggregations. It's really quite straightforward to do them, and they run pretty quickly. So that was our first problem, frequency. Let's move on to our next one, which was attribution, which asked, how much should I pay for ads? Or rather, what is the value of a particular ad? And at the end of the day, most of these problems are the closest. Any problem in this class boils down to the closest thing ad tech has to a religious war. Everybody has their opinions. Everybody has their models. I really try to stay out of it. I try to build the intermediates and the building blocks for analyzing all kinds of different models so that my data scientists can go fight that religious war elsewhere, right? So if we think about most of these models, they actually boil down to something straightforward, which is sessionization, which is a problem as old as the internet, right? Basically, you're trying to look at each user's activity as a timeline and kind of go backwards in time and say, I'm going to start at my conversion, and a conversion can be anything. It can be a purchase, it can be a sign up, it can be requesting a quote. I've represented it with a $sign here visually. And you're going back in time and looking at all the ads and all the activities people took before they bought something to better understand what was the influencer for that purchase. So like I said, on the far right, you have the $sign, and then as you go to the left, you have, for instance, 3 ads that person saw before purchasing. So what does this look like in terms of SQL? It's really straightforward. You join the views onto the conversions such that a conversion happens after an impression, and you make sure it's for the same user, and you move along with your life, right? This basically builds that timeline for all of our users at once. The real challenge is not this. It's what you do on top of this, right? And for us, we basically settled on a class of models that we wanted to analyze called counting models. And these counting models are basically any model that takes into account the proximity of an impression to the final conversion. And we can talk about proximity in 2 different ways concretely. One is the position of an ad relative to the conversion. So we can say that the rank in the timeline is an important thing to analyze. Or we could talk about proximity in terms of time, and usually these 2 things line up, but they're slightly different. You can say, I want to know what the hour offset between the conversion and the impression is, because ads that got shown nearer to the conversion are more valuable in my mental model than others, right? So these are 2 simple enough ideas. Let's see how we implement them on top of the sessionization that I introduced just a moment ago. So there's a lot on this slide, and oh good, it's not cut off. Most of this query is the boilerplate I showed you earlier, right? There's only one part that really matters, and it's that window function at the bottom of the select. Those 2 lines of the code are basically the meat of the whole thing. If you've never messed around with window functions, by the way, please go do that. They're one of the most powerful parts of SQL. Redshift supports them very well. Go out and use them. So basically, those 2 lines are the ones that compute the position argument, and then the date diff before it is what produces the hour offset. So now, assuming I run this in production, it's going to take a couple of 100 billion rows for a quarter of raw impressions and join them to a couple of 100 million rows of conversions, and then annotate them with the hour difference between the conversion and the impression, as well as their position in the timeline. And this outputs single-digit billions of output rows. And we do this in not much time at all, tens of minutes. It really kind of depends on the day. But know that you can do this in about half an hour if you wanted to on data scales of that size. So now we have our sessions table, right, that's been populated by this query. And we would like to know what statistics we can compute on top of it. So you could do something extremely straightforward and naive and say, oh, sorry, that's right. You could basically say, hey, I want to compute what that this certain site appears on average in the nth position of users' timelines, right? And that's just average of position, very straightforward to understand, right? Or I could do something a little more subtle and replicate the last touch attribution model, which gives all of the credit for an ad to the last ad that was shown, or all the credit for a conversion to the last ad that was shown. And so what happens when I evaluate the position equals 1 expression, it gives me a 0 or 1 Boolean flag. And so if you were the last thing in the timeline, you get all the revenue. Great, cool. Or you could do something even more sophisticated and say that on average, before this site, a user sees n distinct sites. Right? So if you have some notion of fatigue, right? Somebody sees an ad, or just the opposite, that it's building up a trust in them that they see this ad across the internet, you could weight things appropriately based on that statistic. So basically, these are some straightforward examples, but pretty much anything the data scientists want, I can implement in here, and pretty quickly. So since I'm only running this portion of the query over those last few single-digit billions of rows, it takes like 10 seconds to run this on a couple of billion rows. And that's really incredible. I can't overstate that. We use dozens of different things in this way. We compute dozens of different statistics, and it runs in 10 seconds. We spend all this time building the sessions table, and then it takes 10 seconds. It's really anticlimactic in a way. So for our production workloads, we basically have 45 days of conversions. We have 90 days worth of impressions because you have to look 45 more days back. We compute about 11 different statistics for all of our clients, and we do that in 2 hours, right? And that's $76 on demand. That's really cool that you can go back and analyze 90 days worth of data in 2 hours on a cluster of that size. So what did we learn from building our attribution query? Well, we found out that window functions are really the bee's knees. We love them. You can sessionize the data with them. You can compute really interesting statistics on top of the sessionized data with them. And the best part of it is it's 2 lines of code. I don't have to worry about the implementation of that. I just tell it what I want, and it does it. And that's pretty magic. I don't know if you've managed software engineering teams, but the devil is in the details. Implementation is always where things get caught up, and this takes a lot of that out. So it's really powerful. Another thing we learned was that if your sort key contains all of the columns that are going to be in your window function, there is very minimal overhead to running a window function on top of enormous tables. In fact, our data science team writes and designs and proposes brand new window functions for use in this query, all without me. They just do it themselves. They send it forward. We do a code review. We run a few tests. But by and large, they're self-serve. And that's really amazing, too. It's increased our productivity drastically. So we talked about attribution. That was our second question. I'm going to move on to our third question, which was overlap, which was the question of how do I reach these people I'm interested in for less money somewhere else? And the question amounts to counting the co-occurrences of people on different sites. Specifically, we'd love to present a table that basically showed you where you saw people on site A versus site, or what people you saw on both site A and site B, and told you which one is cheaper to buy on. So let's walk through this table concretely. You'll notice that's supposed to be lined up on the 90%, but in any case, 90% of the people you see on C, right? That's why it's red. 90% of those people you also see on B, right? So, and that's supposed to be also lined up on the bottom. So I'm actually going to go back a few slides so you can see it clearly. I'm saying that 90% of the people you see on C also appear on B. In addition to that, it costs $9.50 to see those people on C, but it only costs $1.05 to see those people on B. So really, the actionable advice we can take away from this table is that, hey, stop spending money on C, spend money on B. You're going to see the same people anyways. So how do we compute this? Sorry, I'm going to jump ahead here. We compute it with a self-join on the impressions table. But to clarify things mentally for you, I'm going to present this in pieces. So first, we need to know where every person was seen, right? Which site they were seen on, and what's their user ID, right? And then we're going to join this thing onto itself, right? And you'll notice a weird condition here for the join key. It's greater than instead of being an equijoin. And what that does is actually prevents us from computing the diagonal row and the bottom half of the table. I'm not going to get into what you could put in that bottom half of the table. Just know that you don't want to double count, so you need to have this condition there. But you do this self-join. And again, you may be thinking, hey, that intermediate table that you presented in the previous slide is also keyed on user ID. So for a quarter, again, that's 20 billion rows. But again, I'm going to have the same conversation with you about, hey, in real life, it's way more than 20 billion rows because you have to segment by date ranges and campaign and site and so on. And so just like the frequency intermediate, you end up with a table that has 70 billion rows for a quarter that you're going to try to self-join on. And that's a ton of work, right? So what we do is, in the same vein, we materialize this intermediate and speeds things up, and you can incrementally build it, and it has all the right sort keys. I won't bore you with that. The final query amounts to basically taking that intermediate and crushing it down to user ID, site, and campaign, and then self-joining it onto there, and then we widen the aggregation at the bottom there. So for an advertiser for a particular campaign can see what the overlap between the different sites they purchased on was. And that's a big deal, right? This is the fundamental question of where can I go spend less money and get the same reach, right? And sorry, so that was to point out the fact that this is now segmented by campaign in this query rather than just being across all of your campaigns at once. So in production, the workload looks much the same as frequency, right? We spend a minute updating that intermediate. We spend about 15 minutes computing the co-occurrences, right? That self-join is about 15 minutes. And then taking the output of that self-join and aggregating it takes another 50 seconds. So all in all, let's say it's 16 minutes. And that's a pretty good deal for us, 17 minutes. And for our entire workload of, again, 6 date ranges and 3 groupings and blah, 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 again, $96, really cool. And what we learned from doing this was, one, if you correctly sort your self-joins, there's actually very little overhead to them, right? So if we think back to the frequency calculation, that was a simple multi-stage aggregation. There were no joins in there. It's conceptually a simpler query. But what ends up happening is that it runs in about 12 minutes, and this ran in 17 minutes. So it's kind of amazing, it blows my mind, that a well-sorted multi-stage aggregation is actually roughly the same cost as a well-sorted self-join. And if you think about it for a while, you'll realize that because you've sorted it and distributed it properly, there's no shuffling of data. So you just do a bunch of sequential I/O, and you take little blocks of the data, and you basically do a Cartesian product on a small block at a time, so there's no big hash tables in memory. You don't carry a bunch of state around. You can just compute this whole thing incrementally as you scan a row. So conceptually, again, you're scanning this table with some small overhead, a couple of minutes on tens of billions of rows of input. So that's what we learned from computing overlap, and it's particularly useful for us. So we'll go to our fourth and most vexing problem, which was ad hoc queries. And for us, we simply could not afford the distraction from our core product that servicing ad hoc queries would require. You need people, you need time, and then there's always the back and forth with the client that takes up even more of their time. So what we did is we kind of turned the tables around and gave them back their data and said, here, why don't you run the query? And so we created this product called the Data Science Developers Kit, which is basically ETL as a service. We unify all their data streams, we clean it up, we pack it up and ship it out at the event level to them so that they can run whatever analyses they want. And because our ETL systems were already doing most of this work, it was half solved. The next question was to find out what they needed and how to get it to them. And so we identified these 8 fact tables. These are billion row tables, and 33 metadata tables, which you can think of as these little dimension tables, tens of thousands of rows. And between those 8 fact tables and 33 dimension tables, you could answer pretty much any question you had on your advertising data. So what we did is we packed these all up and dropped them in an S3 bucket every day that they could load. Neat, right? Well, not so neat, because you actually have to figure out how to give them exactly their data. You can't ship them somebody else's data. So this is actually quite tricky. If you've run a business, you know that most of your business rules are encoded in a SQL database somewhere. So deciding whether an entity or an event is owned by one client or another is actually a ton of work. And so we started walking back and understanding what all that business logic did, and we found out that there were 42 views in a Postgres database that did 121 joins over 1,100 lines of SQL to figure out what all of our entities and all of our events and who they, the mapping between who owned them and what they were. So the prospect of identically replicating this logic in another system, let alone another system that didn't support SQL, was like, okay, you're in for a real good time. And so we decided, obviously, since I'm giving a talk about Redshift, that, hey, SQL supports Redshift, so let's find a way to get that logic into Redshift, and then we'll use Redshift to perform those joins and get those entities and events out to the user. And so anytime somebody says, I'm going to replicate logic from one database system to another, you should be running for the hills. Ad hoc replication is no joke. It will get you fired sooner than later. But I'm going to show you how you can use a lot of reliable open source tools to actually synchronize, say, something like a Postgres database on premises with Redshift and get that logic in there safely. So we basically took a bunch of open source tools that ship with Postgres, like pgdump and pgrestore. And what we do is we dump a transactionally safe version of the entire database with pgdump. And then using pgrestore in its two different modes, schema only and data only, we export the schema, the DDL that you need to build up all the tables. And then we export all the tables as CSVs. Then we put those in S3, and then we load them into our Redshift clusters, right? And now I have a full transactional copy of all of my metadata and all my business rules and all my views in Redshift in the exact same state that it was in my Postgres database. And so obviously, we do this on a daily basis right before we run all of our analytics. And you could do it more frequently, and you could do it via S3, or you could do something neat like copy from SSH and have your Redshift cluster SSH to your Postgres cluster, and then have it dump these things out. We actually found that having it in S3 is really valuable because you can effectively go back and time travel. You can go in and say, hey, I want an exact snapshot of what happened yesterday so I can debug this problem, or so I can go fix a problem that we had yesterday, right? So you can use all these open source tools. It's a couple hundred lines of code. It's been running for 200-ish days of uptime. For us, it's bulletproof because pgrestore and pgdump and S3 are all bulletproof. So I encourage you to use this technique. It's battle hardened. I know several other companies that do the same thing. So anyways, to round back, we now have all of our data and our metadata replicated into Redshift. We'd like to get some data out for a particular client. Well, that's as simple as a join. So you basically wrap an unload statement around a join on one of your fact tables, and it drops it right into their S3 buckets, and that's pretty magical. And the two assurances that your clients get from this is, one, it's well-formed data, right? It came out of Redshift, which has type safety on the columns, has null safety. You can assert certain things about this in the database. The database will enforce those for you. It's going to be well-structured. I mean, you could load it into Redshift, which is a good idea, or you could load it into any other system. I mean, CSVs are the bread and butter of analytics, right? Everybody's gone through and done CSV analytics, even on their laptop on the command line. And also, since we as a company are doing work on all of our clients' data at once, and we're doing it far more aggressive things than they are usually, we've actually vetted out the scalability of Redshift as a system. So they don't need to go through a whole big process of figuring out which data warehouse they want to use. They just come in the door and they say, oh, you guys are using Redshift and you do it on way more data, so we can use Redshift too. Great. And that puts a lot of people at ease. So unfortunately, I can't tell you how many clients use this, but just know that the workload for the number of clients adds up to about an hour and a half on that same 8x DW2 8x large cluster. It's not that expensive. Running a product like this for $55 a day is a pretty good deal, if you ask me. And the other thing we learned, obviously, is that, hey, if your business logic is in Redshift, is in SQL, keep it in SQL. You can get into Redshift easily and quickly, and there are open source tools that are really easy to compose to build these types of replication systems. So those were our 4 questions. Those were our 4 solutions. Let's talk about how Redshift made this possible and talk from an operational perspective. So if naively we went back through all the slides and looked at the how long do these workloads take and summed them up, we would end up with 8.5 hours of execution time, right? Just naively if we put it together. And that was on that 8 times 8x large SSD nodes, right? So whatever you may say, that's fast, slow, I don't really care, right? We need to deliver our reports in a certain amount of time, but it's not 8.5 hours. We don't have 8.5 hours, right? Because we're working on, a day. By 8 a.m. the next day, we have to have reports for the previous day. And so at best, we have 8 hours. But that ignores the reality of other ETL systems and whatever's on the other end of the Redshift pipeline. So for us, it meant we had 5 hours to do this all. So you say 8.5 hours of execution time, make a bigger cluster, right? Run these workloads on one gigantic cluster. And so I doubled the node count and ran a benchmark. And so I've broken it out by restore time, which means, hey, you have a snapshot, you need to restore it and boot a new cluster every morning. There's an hour of maintenance, which is effectively, hey, load the new day's worth of data and do the updates on the intermediates. And finally, you have the execution time. So what do we see from this? Well, for $691 a day, I can take down my execution time from 8.5 hours to 6 hours, but that's still not my 5-hour deadline. So I've spent a ton of money, right? And I could potentially go double this cluster again and see if it goes faster, but that wasn't the right solution. What we did instead was actually split it out into 4 clusters, right? And so the advantage of this were clear. I mean, obviously, we're now done in under our 5-hour timeline, so that's great. And you'll notice that we actually saved 20% on our total price. And how is that possible, right? Because we're doing double work on a lot of this. We're loading the new day's worth of data on 4 clusters instead of 1 cluster. We're restoring 3 of those clusters instead of 1 cluster. So we're doubling up on a lot of time. But in reality, because we're tailoring certain workloads to certain clusters, and we could scale them independently, we end up saving money. So that's one huge operational advantage. The other operational advantage of splitting out workloads this way is that if your monolithic cluster goes down for any reason, hey, now all 4 of your reporting workloads are late, right? Instead of, hey, we had 1 cluster go down, so just that 1 workload is late. And it's really valuable to us to know that we have this kind of independence of workloads. And then second of all, let's say you're migrating from one region to another, or you're failing over from one region to another. To be able to fail over workloads one at a time is extremely valuable and really opens up a lot of windows operationally, right? So the lessons we learned from operating Amazon Redshift actually have nothing to do with the workloads. The impressive thing about Redshift is that they've taken this thing that was typically impossible to operate or really unwieldy to operate, to provision, to deploy, and so on, to orchestrate, and they've made it easy. And so that made us rethink holistically how we design these systems, right? I know now that no matter how many workloads or platforms or products I come up with that are different from each other, I can run them in parallel, and I'm probably going to save money. So my parting piece of advice to all of you is to go out there and experiment aggressively with breaking out your workloads in different Redshift clusters. Run the experiments. They don't cost that much. And they certainly opened our eyes to an incredible set of product opportunities that weren't possible in the past. So thank you.